In this video, I'm going to show you how to use the fundamental theorem of algebra with cubic equations. So let's start with the refresher of the fundamental theorem of algebra. The fundamental theorem of algebra just says that every nth degree polynomial with real coefficients has n roots in the complex numbers, if we're counting repeated roots separately. Now, the big insight is going to happen when we pair this fundamental theorem of algebra with a fact about roots. The fact about roots is that non-real roots occur in pairs, meaning that if some complex root a plus bi is a root, then so is its conjugate a minus bi, and they have to have the same multiplicity. So, for example, that means that if 1 plus 2i is a root, then so is 1 minus 2i. Likewise, if 1 minus 2i is a root, then so is 1 plus 2i. They either occur together or not at all. Furthermore, they have to have the same multiplicity. For example, if one of these roots is a double root, then so is the other root. But that'll only happen for quartics or higher order polynomials, which we'll consider later. Alright, so when we pair these two ideas here, we get a conclusion that every cubic polynomial has either 1 or 3 real roots, counting repeated roots separately. Now let's talk about why that is the case. How do we get from these two ideas to this conclusion? Well, why don't we start out with one fact. And our fact is going to be that the number of total roots of a polynomial is equal to the number of real roots plus the number of non-real roots. For a cubic polynomial in particular, according to the fundamental theorem of algebra, we know that a third-degree polynomial, a cubic polynomial, with real coefficients has to have 3 roots, so the number of total roots has to be 3. We also know that non-real roots have to occur in pairs. So we either have either 0 non-real roots or 2 non-real roots. So now just doing some simple algebra, if we have 3 total roots, 0 of which are non-real, then 3 of them have to be real. Or if we have 3 total roots and 2 of them are non-real, then 1 of them has to be real to sum to 3. So there we go. Every cubic polynomial has either 1 or 3 real roots. Now let's go through the cases of 3 real roots and of 1 real root. As we go through these cases, we're only going to consider positive cubics, but the same argument is going to work for negative cubics as well. So the first case of 3 real roots is going to be when all roots are distinct. So we'll have 3 distinct real roots. And an easy example of that would just be to choose the roots 1, 2, and 3. So we could define a polynomial x minus 1, x minus 2, x minus 3. So the roots here just come from setting each factor equal to 0. So the roots are just 1, 2, 3. Let's go ahead and plot those on our graph. 1, 2, 3. And according to the end behavior, since this is a positive leading coefficient, as x increases, so should the polynomial, so it should go up from here, and as x decreases, so should the polynomial, so go down from there, and then we can just connect the rest of it. Looks something like that. Okay, so that looks pretty familiar. What are the other cases? Well, another case is 1 distinct and 1 repeated root. Now, an example of a polynomial having 1 distinct and 1 repeated root could be just x minus 1 times x minus 2 squared. If we write all of the repeated roots separately, then we just have x minus 1, x minus 2, and then times another x minus 2, because that root is squared, and then the roots here are just 1, 2, and 2. So 2 is the repeated root, and 1 is the distinct root. So what would this look like on a graph? Well, again, we have the root at 1 and the root at 2. And we've got, since it's a positive leading coefficient, there's positive end behavior. As x goes to infinity, so does the function. So it goes up like this way, and same way as it goes down. So something like that. And then remember, at repeated roots, when the multiplicity is even, like we have here, there are 2 instances of the root 2, the function doubles back on itself. So it goes up and then back down through the root of 1. All right, so we've got these 2 cases. There's one more case. The last case is one triple root. In other words, a root that itself is repeated 3 times. The easiest example of a triple root would probably just be x minus 1 cubed. When we expand that out, we get x minus 1, x minus 1, x minus 1 all multiplied together. Roots are 1, 1, and 1, so the root 1 occurs 3 times, has multiplicity 3. So if we draw a graph of this, there's going to be a root of 1, and since it's a leading coefficient that's positive, as x goes to infinity, so does the function, and as x goes to negative infinity, so does the function. That also makes sense because odd multiplicity, the function goes straight through the roots. Alright, now let's think about the case of one real root, and let's start out by thinking about this graphically. If there is just one real root, there's only one possibility for the graph of the function. The function is going to go right through that real root. So why don't we say that there's a real root at 1, and then the function is just going to go right through that, like this and that. Okay, so we've got our one real root, and now let's try to write a polynomial that corresponds to this one real root. So we'll start out with a factor that's x minus 1, and that corresponds to the single real root. So now we need to figure out what to multiply this x minus 1 by so that we remain with one real root. We don't want to introduce any more real roots, and we don't want to introduce any repeated roots at 1 because we want a single real root, a distinct real root. The trick is to multiply this by a quadratic factor which has no real solutions. So how about x squared plus 1? There's no real number that you can square and then add to 1 and get 0. Rather, this factor x squared plus 1 has 2 non-real roots. So this is really a case of one real root and then 2 non-real roots, still summing up to 3 roots in total. And to be absolutely explicit about this, why don't we even solve for what are the roots of x squared plus 1? So we know that x minus 1, to find out what the root of that is, we just do x minus 1 equals 0, and then add 1 to both sides, get x equals 1. And so let's do the same thing for x squared plus 1 equals 0. Well, subtracting 1 for both sides, we just get x squared equals negative 1, and then taking the square root, x equals plus or minus square root of negative 1. And so that means x equals plus or minus square root of negative 1. We just call that I, and that's imaginary. So there are 2 non-real roots. Our 2 non-real roots are x equals I and x equals negative I. And that also makes sense because we know that non-real roots come in pairs of their complex conjugates. I and negative I are the conjugates. Now, before we go on, let's just emphasize that these 4 cases right here, these are the only cases for a cubic polynomial. If you don't believe it or you're skeptical, then try drawing a cubic curve that doesn't fall into one of these 4 cases outlined here. It's impossible. Alright, in light of the previous slide, let's do an example. So we're given that x equals 1 is a root of this cubic equation, x cubed plus x squared plus 3x minus 5 equals 0, and we want to find all the roots. Okay, so we know from before that cubic equations have either 1 or 3 real roots, counting repeated roots separately, so we should expect that at the end when we find all the real roots, either this will be the only real root or we'll have 2 more real roots for a total of 3 real roots. Okay, so that's what we're expecting based on the previous slide, but how do we actually find all the roots? Well, we'll notice that since x equals 1 is a root, then we should have a factor that goes x minus 1. X equals 1 will be the root corresponding to that factor. And then since it's a cubic equation here, then we'll need a quadratic factor for the other factor. So x minus 1 times some quadratic factor is equal to 0, and then the remaining roots we'll find from the quadratic factor. Okay, so how do we find the quadratic factor? Well, we can just divide this polynomial here by the root x minus 1. So why don't we do that? We'll set up a synthetic division. We'll put the coefficients of that polynomial, 1 for x cubed, 1 for x squared, 3x, and then minus 5 at the end, and then we'll take that x equals 1 is a root, so we put 1 up here, and we can go ahead and divide. Okay, so start it off with 0, add down the column, 1 times 1 is 1, add down the column, 2 times 1 is 2, then add down the column, 5, then times 1 is 5, add down the column, 0, good, so no remainder, and then our quadratic then is just 1x squared plus 2x plus 5 with no remainder. Okay, there we go. So we can write this again as x minus 1 times that quadratic, x squared plus 2x plus 5 equals 0. And now we can go ahead and set each factor equal to 0. So of course this first factor, x minus 1 equals 0, that just comes from our root x equals 1, so that's no surprise there. But the quadratic set that equal to 0, and we'll find our remaining roots. So x squared plus 2x plus 5 equals 0. Can we factor this at all? Doesn't look too good. So why don't we just go ahead and use the quadratic equation. X equals negative b, so negative 2, then plus or minus root of b squared, so 2 squared, which is 4, then minus 4 times a, which is 1, times c, which is 5, all right, all over 2. So x equals negative 2 plus or minus root of 4 minus this whole thing, 4 times 1 times 5, that's just minus 20. So root of 4 minus 20, root of negative 16, all over 2. So x equals negative 2 plus or minus, well, root of 16 is just 4, but we've got a negative in there, so I all over 2, so x equals negative 1 plus or minus 2i. So there we go, there's our other roots. We'll just write it out separately. X equals negative 1 plus 2i, and then x equals negative 1 minus 2i. So there we go, there's our roots, and that matches up pretty well with what we were expecting. We were expecting either one real root or 3 real roots, and indeed we just have one real root, the other 2 have imaginary parts. Here's a final example. The following Argand diagram displays the roots of a cubic polynomial p of x in the complex plane. So I've got a diagram here, the real imaginary plane, and each of these dots corresponds to a root of our polynomial p of x, and p of x is a cubic. Okay, so if the leading coefficient of p of x is 1, then what is p of x? So we're given information about the roots. We know the leading coefficient is 1. We know it's a cubic. And what is this polynomial then? How can we figure out what it is? Okay, so let's gather some of this information. Its leading coefficient is 1, and it's a cubic polynomial. So that tells us that p of x goes like this. It's equal to x minus a times x minus b times x minus c, where these are the roots of the polynomial. A, b, and c are the roots, 3 factors, 3 roots, and so there's 3 factors. That makes it a cubic, and also if you multiply all this out, you'll get just an x cubed at the beginning as a leading coefficient, which does have a leading coefficient of 1. So this is the form, and we want to use this diagram to plug in for what are these roots here. Okay, so in this diagram, each of these points corresponds to a root that will plug in for a, b, and c, but let's figure out how to read this diagram off. So each point on the diagram, each point, let's write that here, each point x, y corresponds to a complex number x plus I, y. So let's go ahead and label the points. This is the point 1, 0, so that corresponds to the complex number 1 plus I times 0, which is just 1, because that cancels out 0i. So this is just 1, and then this point right here, that's the point 0, 1, which corresponds to the complex number 0 plus I times 1, which is just equal to I. And then this point right here, that's 0, negative 1, which corresponds to the number 0 plus I times negative 1, or just negative I. Okay, so I, 1, and negative I are our roots that are shown in the plane here, and let's go ahead and plug these in. So how about let's plug in 1 for the first root. So 1 will go in for a, so we'll have x minus 1, and then for b we'll plug in, how about I here, x minus I, and then for c we'll plug in negative I. How about that? X minus negative I. And let's just go ahead and simplify this. So x minus 1, x minus I, and then x minus negative I, that's just x plus I. And now we can go ahead and multiply out. Let's take care of the imaginary parts first. So x minus 1, and let's multiply this out. So this is a perfect difference of squares. So this is x squared, then minus I squared. So x minus 1, that's just x squared minus negative 1. So x minus 1 times x squared plus 1. And then we multiply that out. We get first x times x squared is x cubed. Then negative 1 times x squared is minus x squared. Then x times 1 is plus x. Then negative 1 times 1 minus 1. And there we go. That's our polynomial p of x. That's what p of x is equal to then. In this video, we focused on using the fundamental theorem of algebra to deduce things about the roots of cubic polynomials. In the future, though, we'll also see how to use the fundamental theorem of algebra to deduce things about the roots of quadratics.